In this tutorial, I'm going to go over information contained in Section 5 of the Pilot's Operating Handbook for the Cessna 172S, which covers the aircraft performance. As always, we begin with the table of contents, which has all the information to be discussed. Next, we have a blank page, which should say intentionally left blank. Here we have the introduction, and it says that the performance data charts on the following pages are presented so that you may know what to expect from the airplane under various conditions and to facilitate the planning of flights in detail with reasonable accuracy. The data in the charts has been computed from actual flight tests with the airplane and engine in good condition and using average piloting techniques. Be a little bit careful here because average piloting techniques done by a professional test pilot whose job it is to make the airplane perform at its absolute maximum limits. So if that pilot can take the Cessna 172 off in a takeoff distance of 600 feet, it's more likely that you, the average pilot, are going to take off that same airplane in 600 or 650 feet. So keep in mind, you want to give yourself 5 to 10% increase in margins so you can be more conservative in what you expect the airplane to do because you're not a test pilot. It then goes on to say, it should be noted that performance information presented in the range and endurance profile charts allows for 45-minute reserve fuel at the specified power setting. And that's because you need to have 30 minutes reserve daytime VFR, and of course 45 minutes reserve for nighttime VFR. And we also see that it says fuel flow data for cruise is based on the recommended lean mixture settings at all altitudes. So it's very critical that you properly lean the engine if you're going to rely on this data. Some intermediate variables, such as mixture leaning technique, fuel metering characteristics, engine and propeller condition, and air turbulence, may account for variations of 10% or more in the range and endurance. Therefore, it is important to utilize all available information to estimate the fuel required for the particular flight and to flight plan in a conservative manner. And here we go on to see the use of the performance charts, which states that performance data is presented in tabular or graphical form to illustrate the effect of different variables. Sufficiently detailed information is provided in the tables so that conservative values can be selected and used to determine the particular performance figure with reasonable accuracy. So now let's go on. And here we can see a sample problem that they do. I won't go over it, but you're welcome to look at it. And here we can see the sample problem where they're doing takeoff. Here is a sample problem for cruise. And here's a sample problem for fuel required. And remember, we're going to want to use our E6B flight computer to help us out as we're doing these calculations. You could use Google. You could use a pocket calculator. But if you want to be proficient, it's better to do it with the E6B every time, just because you get into the force of habit of using it. Here they're calculating the fuel required. Here they're doing a sample problem for landing. And it says, demonstrated operating temperature. Satisfactory engine cooling has been demonstrated for this airplane with outside air temperature 23 degrees above standard. And here's a case where we kind of go back to the first section where I told you those definitions are important to know because, well, what's standard? And in Section 1, we define standard to be 15 degrees Celsius. So here, the airplane is rated for 15 plus 23, or 38 degrees Celsius total. And references should be made to Section 2 for engine operating limitations. Here we can see airspeed calibration, which allows you to adjust the indicated airspeed, or KIAS value, to the calibrated airspeed, or KCAS value. And that's because the pitot probe has some distortions in the flow field as the air is flowing around it, and these calibrations give you a more precise measurement of what your airspeed is. But in practice, we really don't use any correction tables like this in the airplane, because particularly when you're at those low speeds, you're usually on takeoff or landing. You really don't have time to do any of these corrections. So the nice thing to know is that the variation you can see is pretty small. It's 1 or 2 knots difference. So just keep that in mind and keep your airspeed 1 or 2 knots a little bit above what you normally would if you care about the calibrated airspeed. And here we can see the same thing. Here we can see a temperature conversion chart, but you've got one on your E6B, so you don't need to use this, but you can if you want to. Here we see the stall speed at 2,550 pounds, and it says here the condition is power idle, and it says for rearward center of gravity, so the most unstable, and most forward center of gravity, or the most stable condition. And we can see what the stall speeds are and how they vary for various flap settings. Now here's an important note. It says altitude loss during stall recovery can be as much as 230 feet, and knots indicated airspeed values are approximate. Here we can see the crosswind component. Basically what this does is allow us to compute what will be the component of crosswind when we take off or land at our departure or destination airport. And we can do that on the ground.